All right, before we get started, did they have any questions from anything from last time, anything at all? All right, let's go ahead and get into it. So still in section 1.3, talking about how to find the limit of a function. So I think we did a few examples on Friday. I do not think we got into this one, right? Okay. So what kind of techniques do we take on Friday to make these estimates? Or what's something we can try here? But yeah, I'm sorry. Okay. There it goes. So what are some good values we can try? Yeah, as t goes to 0. Okay. 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 Actually, they're going to be different, aren't they? And while I'm writing these out, if anybody has a calculator, start getting me some numbers. But while we're doing this, hopefully, hopefully you're seeing how kind of daunting and tedious this is, and know that we're going to eventually move on to more sophisticated and better techniques. This first one I got, we'll just go 5 decimal places, 16662. Let's get at least a couple more before we come to a conclusion. Actually, these are all going to be identical in pairs, aren't they? Oh, that's not the right one. Do we see why I'm saying these are equal? So if I'm squaring all these numbers, it really doesn't matter if I square. What? I'm going to assume that there are 3 in there. Okay, that's probably enough. Does anybody recognize? So I've got a lot of good decimal representations here. What do we think we're going toward? Do we recognize what this number is? Go ahead. What's that? 6. That's 6, yeah. Which this limit is indeed 1/6. Any questions? For finding limits, but I just kind of want to get us all in the right mind frame of kind of what we're looking at, how we do it, what they mean. Any questions before I move on? Okay. How about this one? So I did not ask it in the last one, but is this one defined at t equals 0? No. How about this one? Is this defined at x equals 0? No. The same kind of thing here. And I'm just really going to replicate the table we just used. I think we had a 10th, a 100th, and a 1,000th. And this time I cannot. And just to get us all consistent, let's do this. Let's say that these are measured in radians. Let's get one more pair of these, even though you might. Has anyone ever seen this particular limit before? One of you? And even if you haven't, you might already kind of know what the limit is going to be just from that one pair of data points, but let's get at least one more. What do we think this limit is just based on those 4 data points? Okay. So when you say 0.999, do you mean like an infinite number of nines? And we don't need to go into why that's true, but that is equal to 1. If you just have a string of repeating nines. But yeah, either way, yeah, the limit is 1. So another way to think about this is, so we're looking at very, very small values of x, right? You know, both on the positive side of 0 and the negative side of 0. When you take the sign of those kinds of quantities, what are you getting? Maybe it's easier to start with this. What is the sign of 0? Sign of 0 is not 1. Sign of 0 is 0, right? So if you take very small, like if you just deviate from 0 a little bit, you're still going to get very small numbers, either positive or negative. So not by any means a proof, but hopefully it kind of makes a little more intuitive sense why that limit ends up being 1. Any questions here? Okay. This is a good one to talk about. So again, hopefully you're seeing that this is not going to be defined where x equals 0. But we can still talk about this limit. So our base point is still 0, so might as well keep looking at the same table of values. It'll be a little easier to compute, hopefully. In fact, it's so easy to compute that somebody would probably shout something out before I even get done writing this down. What is 1 over 0.1 squared? $100? About 1 over 0.01 squared. 10,000. This next one should be, and really these are going to just match up in pairs. And hopefully for this one, you're going to get 1,000,000, 1 times 10 to the 6th. So what is happening to this function as x gets closer and closer to 0? Well, man, I know what you're getting at. So do you understand why I'm fighting back if he reaches infinity? So the infinity is not really, like, it's not a value. It's not something we can. But is there going to be a maximum value that I hit as my x values get closer and closer to 0? No. So what does that mean for this limit? Does it exist? It does not exist. So, and there's a couple ways we can say that. So I'll write them both out. The limit as x approaches 0, 1 over x squared. This abbreviation is pretty common, does not exist. Or sometimes you'll see this, which is kind of, it's just a more specific way to say the first one. So you're right, the limit is infinity. If you give me, you can give me as large of a positive number as you want, and I will be able to find an x value that delivers that. So there is no like upper bound, there is no maximum to this function. The limit is infinity. When I was first learning Calc 1, I remember that, you know, when you see something, oh, the limit equals something, even if it's infinity, it exists. In this case, that's not true. It does not equal a number, it equals infinity. Basically, I'm just telling you that it gets arbitrarily large. So I'm telling you the limit doesn't exist, but I'm giving you some specific, some detail about how that function behaves. And I think this is the first one we've looked at where the limit doesn't truly exist. So definitely worth looking at. Worth talking about if you have any questions. How are we doing with this one? Happy? All right. All right, this guy. So I know I got quite a few engineering majors in here. Has anybody ever heard of the Heaviside function? The Heaviside function? It's named after the engineer who came up with this. But basically, if t is a negative value, then my function is valued at 0. If t is a 0 or a positive number, then my function is valued at 1. So if I were to draw a graph of this thing, and while I mentioned engineering, those of you who are, if any of you are electrical engineers in particular, you'll make a lot of use of this. So for any negative value, this thing is 0, but not at 0. And then starting at 0, function takes a value of 1. So what I'm asking now is, what is the limit as t approaches 0 of this function? Okay, I got 1 vote for doesn't exist. 2 votes, many votes, no one's going the other way here. Okay, so this limit does not exist because, and just tell me why. And I think a lot of us have the same thought. Let's put it into words. Go ahead. Doesn't agree on that side of the so far, I have not dealing with something called two-sided. Our function needs to agree. Basically, as I approach so my base point here is 0. As I approach my base point from values less than it, from the left, I need to approach the same value as I do when I approach from the right, or from numbers that are larger. And in this case, you can see that doesn't happen. Definitely matters on which side I approach my base point from. So this limit, I did this for a reason, this does not exist. But it's a good jumping off point to talk about this idea here. So we have things called left-hand limits and right-hand limits, and I went too far. So left-hand limit, very, very small modification to the notation. So pay attention to this, this superscript here on my base point. Unless you've seen it previously, until now, there's been no superscript there because I am not being specific. I want to know what happens as I approach that base point from either side. And now I want to know what happens when I approach that base point from only the left. So I am only going to look at what happens when I begin with x values that are less than a and get as close to a as I want to. So you read that as the limit as f of x approaches x from the left, or the left-hand limit. Those are both totally universally accepted. But the bottom line is I am only looking at values of x that are smaller than a, whatever my base point is. Have most of you seen this one before? Okay. Right-hand limit is, if you're understanding left-hand limit, the right-hand limit is pretty intuitive from there. In this case, I'm only looking at x values that are larger than my base point a. While people are writing, I'll just ask, has anyone tried to get my notes from Canvas? Either the ones that before I mark them up or after? Okay. Really? Okay. Okay. Yeah, I would recommend downloading it just because they are PowerPoint. So I think if you're using an Apple machine, or maybe even if you're not, yeah. I know for most of what I do on Canvas, regardless of what kind of document or what kind of file it is, the preview isn't totally reliable. Okay, so now that we've talked about one-sided limits a little bit, let's go back to, or sorry, one more thing here. And somebody already mentioned this. The two-sided limit of a function only exists if the one-sided limits agree. Kind of implicit in that I'll note is that when you're looking at a limit, you really should be looking at both sides if that's what it calls for. And the reason I bring that up is for some of the examples we did today, and even some of the ones we did on Friday, we could have very easily just looked at numbers that were larger than our base point, and we probably would have come up with the right limit. But you definitely should do values on both sides of the base point. All right, so let's go back to this Heaviside function. I don't think I wrote out that name on the last one here. Heaviside. So now that we have talked about this idea, we can be a little more explicit about the limits on this guy. So that first limit, I'm not going to read it out to you because I think that's need to make sure that you understand what the notation means. But what value should I give this guy here? This one is 0. How do we feel about that answer? If that one's 0, what's our next one? 1. And we already said that this thing doesn't exist. We agree with all three of those. So just to kind of drive the point home, so this Heaviside function takes negative values when my value of t is negative. So as I approach 0 from only negative values, then all of those values are going to be 0. Because I'm like in this case, it's kind of easier to see. As I approach from the left, I'm not even getting closer and closer and closer to 0. All those values are 0. And similarly, that's why the limit from the right is 1. I guess one more thing I will say in here that I should have put in the slides is this. What's this equal to? 1. So not that it really has anything to do with any limits, as we've said in the past. Those things could be totally different. If I wanted to, I could define this function. Actually, sometimes you will see this function defined as where when t equals 0, the function's equal to 1/2. It's not very common, but sometimes some places you'll see that representation. But it's not going to change what these limits are. Any questions here on our first one-sided limit example? Okay. So let's take a look at all of these. So give you all a chance to think about those 8 different expressions, and then I'll get some answers from you. All right, let's go for it. How about this first one? All right, go ahead. 3. And how about the next one? Go ahead. 1. Oh, I should pause there, make sure we agree, we understand why that's the case. Any questions on those first 2? All right, because, and hopefully, if I give you those first 2 values, do you even need to look at the graph to answer this next one? No. What must this next one be? Doesn't exist. And why is that? They don't agree. So yeah, for the 2-sided limit to exist, the 1-sided limits have to deliver the same result. Okay, so I think we understand what's going on around our base point of 2. How about the base point of 5? What is that first limit? Go ahead in the back. 2. All right, the limit from the left is 2. How about the limit from the right? What? 2. And again, do I even need to look at the graph to figure out this next one? No. What is it? So yeah, if they agree, then that's the 2-sided limit. All right, so these next 2, I'm not talking about limits. What is g of 2? That doesn't exist, right? It's not defined. And how about g of 5? 1. And just to hammer them, and I think those are both good to see because, and the reason I keep harping on this, and it's not because I don't think you're not getting it or whatever, how many negatives I had in there. It's an easy thing to get tripped up by, not just for those of you who are just kind of seeing this, not for the first time, but you're still kind of new to it, but for anybody. Yeah, the function's value has nothing really to do with the limits around that base point. Go ahead. No, those are totally fine. Yeah. That one takes me a lot less time. That's really the only reason I go for it. Any other questions here? Okay, I think that is it for 1-3. So let's talk briefly about this homework, that web work set for 1-3. In general, is 2 days beyond when we finish it in here? Is that a fair deadline? So if I made this due Wednesday at like 11:59? Okay, cool. We'll stick with that pattern by default, and then we'll revisit if we have to. And one thing I do want to bring up again, my deadlines kind of just like with the state of the world have to be fluid. So if you're not feeling well, or you feel like if you're not feeling well, whether that means you can't come to class or maybe you're feeling so poorly you just can't get to work, please let me know and I'll work with you. But I've already had classmates who've had to kind of call out from stuff, even if they're not feeling poorly. But just yeah, keep me posted on those kind of things. So I'll go ahead and get rid of 1-3. So 1-4, calculating limits. So like I said, we're doing kind of the really, really like unsophisticated approach to finding these limits for section 1-3. Now let's put some more thought behind it. Before that, so these are technically things we haven't really talked about yet, but let's kind of talk about what happens if we make some changes to our function. I'm telling you our base point x equals 1. I'm giving you limits of 2 different functions at that base point. So from there, the limit of this new function, f minus g. I'm going to vote for 1. I got to vote for 4. And like I said, I'm asking you these before I tell you kind of how this works. So just kind of want to see what you think. Got another vote for 4. Those of you who are saying 4, who wants to give me some reasoning behind that? Go ahead. Right. And that's basically true. Think of it like let's say you had the graph of F and the graph of G. How would you graph F plus G? And you would just take a bunch of points, add them up, and then plot those new points, right? So, if I do that, then basically whatever I'm approaching in both these functions, I can take their difference, because that's really what I'm doing when I'm subtracting those functions. I said adding, but really just subtracting. Oh, let's go back. So yeah, this is indeed 4. And I'm not sure how long it's been since you've done your transformation of functions type stuff, but it's essentially what I'm doing here. How about this limit of 5 of f of x? Go ahead. 15, yeah. Same kind of rationale. If I was going to graph the function 5f from f, I would just really take all the y values and scale them up by 5. And finally, the limit as x approaches 1 of g of x over f of x. I got to vote for negative 1/3. By body language, I'm going to guess that we're not quite as sure about that one. Yeah. No, these are all good. And the division gets a little weird. Does anyone know why they're a little sketchy on the division part of this one? Are there cases when I couldn't simply divided by 0 is a thing. Obviously, that's not a concern here, but I think the very fact that is a concern might have given you some pause. So let's talk about these limit laws. Because you're going to make a lot of use of these. If you can break a complicated function into 3 or 4 smaller ones, less complicated ones, that's usually going to be a lot easier to analyze and think about. So for some base point A, let's say my limit of the function f is L, limit of function g is m, and c is just some generic constant. So we kind of already saw these. So based on what we just did, what is the limit of f of x plus g of x going to be? L plus m. So sum and difference work hopefully in an intuitive way. If I know the limits of those individual functions, I can think of sum or difference, and that's always going to be true. How about that constant multiple? That'd be lowercase c times capital. So those first two I just asked you about didn't seem to, whether or not you gave me a response, I didn't see the, squirming in your chair that I saw in the third bullet. All right. Couple more. So product rule and quotient rule did not give you. What do you think that limit's equal to if I just take the 2 functions together and make a new function by multiplying functions together? The limit will just be lm. And similarly, how about this bottom one? L over m. Provided that what? M is not 0. Otherwise, you're fine. So I mean, that's the only real contingency you got to worry about is with divided by 0. right. Be mad at me. Powers and roots. So if I were to take a function, my function g, and basically make a new function by raising it to the whatever, the fifth power, the nth power. I know my limit as x approaches a of g of x is m. What's this new limit going to be? M to the n, yep. And I'm hoping that these are a lot of these are intuitive. If you want to see any of these things like proven out rigorously, those things are out there, or I can do it for you, but hopefully they're making intuitive sense so far. How about for that root? Nth root of L, or if you prefer, anything we have to worry about with that one. I just realized that I forgot to put a disclaimer on this one. And really, it goes for both of these. What if the limit of f of x as x approaches a is -4? And I want to take the square root of that. So watch for undefined. And really, that can happen with the power. No reason the power has to be a positive number or a whole number. With the power or the root? Let's say, for example, let's say the limit as x approaches a of f of x is -1. Then what's the limit as x approaches a of f of x to the power of 1/2? So based on the law I just gave you, that'd be the square root of -1, which is not real. Good question, though. Thank you. Anybody else? Go ahead. You can, but I is not a real number. And that's one of the, it's one of those things in math. If I go back in time and change the name of real versus imaginary, both those things are absolutely real. And I think the name really does that a disservice. But we're talking about real numbers. We're talking about, yeah, no imaginary component. Good questions. Anybody else? Okay. And constants and identity. These are deceptively mysterious. I think it's worth talking about them. What's the limit as x approaches a of c? C. Yeah, I'm not even involving functions at that point. What's the limit as x approaches a of x? Not x. It's a. And kind of I'm going to phrase this in a way that's going to make it sound kind of dumb, but it's cryptic in how simple it is. As x gets closer and closer to a, what's x getting closer and closer to? That's really what that notation is asking. And the reason I bring it up is because, we're using these limit laws as kind of these weapons to break up these complicated functions into smaller things. And sometimes the small things you're going to get is you're looking at the function x. All right. Let's look at one here. The limit as x approaches 5 of this thing here. So can I start breaking this thing down into smaller and smaller limits? Who wants to make the first breakdown here? Go ahead. What's that? You could. I think you could, but yeah, let's not worry about that. I mean, you definitely could do that, but I think there are perhaps simpler ways we can do this. Go ahead. Yeah. Yeah. And as long as we're doing that, let's just, you can do one of those for each term. We may not need to really calculate this, but since this is our first time kind of going through this, let's kind of just tear it down as much as we can. What else can we do?
Last one.
The last one's just 4. This is that. Yeah, it's a constant. Yep. So that one I'll just bring down to 4 with. How about these other two terms? That, go ahead. Right. So we know that these things are all going to be well defined. Right. And which I will do at the end. Like I said, I'm probably kind of like getting into the detail, or more into the details here than you would normally, but just kind of want to show how these laws work. Yep. So, and I'm going to kind of I'll do that to both of these, but I'll just kind of break it down like this. 2 times the limit of x approaches 5 of x squared minus 3 times the limit as x approaches 5 of x. And I'll take the last move on this one. This is equal to 2 times this limit, the limit as x approaches 5 of x. That whole thing squared. And I think this is probably enough. But here's kind of the power of that identity rule. Is like, I know that, as x is getting closer and closer to 5, yes, x is getting closer and closer to 5. That limit obviously exists because I'm taking x values that kind of continuously approach 5, and that happens to be kind of the output that I'm looking for on the other end as well. So this should be 2 times what?
25.
Yep, or I'll just be real granular with it. Minus 3 times 5 plus 4, which I'm sure it's not surprising to some of you that, yes, I very well could have just evaluated f of 5 to start this. Is that 50 minus 15 plus 4? So 9. Any questions on basically how we applied those laws there? Go ahead. Not always, no. And this is one of those cases where you very well could have. But no, that doesn't always work. And that's kind of goes back to the, I've said it a bunch of times, but I think we need to see examples of why it doesn't always work. The limit as x approaches 5 of this function, or of some function, and let's call some other function g. These two things it's very possible for these things to be simultaneous. I don't know what that function, I don't know how that function could have come about, or you know, where it might come from, but that's totally possible. I could have a function who has a limit at that base point of 2, but it's not defined. The value of the function is not 2. What kind of function is this that we just dealt with? It's a quadratic. I was thinking a little more general. It's a polynomial. We have a really good idea of how polynomials act, and you know they're a kind of function that really you know the limit is going to be what the value of the function is everywhere. We'll talk a little more about that as we go on. How about this guy here? Or you know, let me actually, for your benefit, I'll say this. We haven't talked about continuity yet, have we? I have to pause. So this kind of thing here, based on kind of what we just said about polynomials, could I just plug in -2 to the numerator here and get that limit? I got one audible yes. I got some head shakes. I got a thumbs up. What kind of function is that in the numerator here? Sorry, just the numerator. Polynomial. So you're right. The whole thing's a rational function because the numerator and denominator are both polynomials. So I know that I can look at polynomials in a very straightforward way. I know that their limit is equal to what the function is valued at that point. So one breakdown I'll do here is this: the limit as x approaches -2, x cubed plus 2x squared minus 1 over the limit as x approaches -2 of 5 minus 3x. So I've written that down, but there's really something else we should have made sure of before I started claiming that these things were equal. Okay, so that's a good thing to look at. Is the denominator going to be 0? No. Okay, so we're okay. So just one more time, I'll break one of these down. I'll do it this time. I think you kind of saw how this worked last time, but I can definitely do this. This one is a constant. I'm just going to leave it alone. Yeah, in this case, when I got all the way down to the identity log, thing I really understand and is really predictable. So I can just start plugging in. -2 cubed is -8. 2 times 4 is 8. I believe that's true. Unless you found an error there. Any questions here? Absolutely. Yeah. Oh, sorry, that was not that. It was that. Oh, go ahead and yeah, keep asking me while I figure out my problem here. Eventually, yeah. And I'm kind of spoiling things for me from a couple days from now, but yes, in this situation, you very much can just plug in -2, but that is absolutely not.
there a set rule saying that when we plug in the limit or when we cannot?
Yeah, which I same. I'm gonna break those things down for you. We'll talk about it then.
Okay.
But yeah, polynomials and rational functions, I'll give you right now that those are continuous everywhere, which means I can evaluate their limits in a pretty easy way. Those of you who kind of know what continuity is, I probably know what I'm going to talk about then, but there's time for that. All right, one more thing I want to talk about before I let you go. Just a quick question here. I think it's quick anyway. So I'm giving you the limit as x approaches 4 of f of x is 1. The limit as x approaches 4. Actually, this makes no sense. I meant for this to happen. This limit is 0, and the limit as x approaches 4 of g of x is infinity. What is the limit as x approaches 4 of f of x g of x? Yeah, I got a lot of votes for 0. Any votes for anything else? I got one for vote for does not exist. So when I was giving you those limit laws, what has to be true for any of those laws to make any sense? Both those limits have to exist, right? Both the limit as x approaches the base point of f and the limit as x approaches the base point of g. So yes, I totally understand. And obviously, to all of us, it's tempting why you'd think this is 0. But this right here, this doesn't exist. And I'll give you an example here. I know the limit as x approaches 0 of x is 0. And the limit as x approaches 0 of 1 over x is infinity. Let's just say 0 from the right. Would you agree with both of those statements? But what's the limit of this? What's the limit as x approaches 0 from the right of this product? X times 1 over x. Well, what is x times 1 over x? So it's the limit as x approaches 0 from the right of 1. So here's the danger. Like it's really tempting to just charge ahead and use those limit laws, but make sure you meet the qualifications. Make sure your individual limits of your individual functions are all well defined. Because you all voted 0, or sorry, a lot of you voted 0. Somebody voted does not exist, and I came up with an example that does neither one of those things. So you have to have those individual limits exist, otherwise you really can't rely on this for anything. Make sense? All right, I will see you all Wednesday. Thank you, everyone.